Let's begin.
We are very, very happy to have Ashok, our old friend, back, even remotely. And he's going to tell us about this very interesting recent development he has been leading last couple of years about how to deal with D-instanton exactly. So let's welcome Ashok.
Okay, thank you very much. Let me start sharing screen. Okay, can you see my screen? Okay.
Yes.
Yeah. Okay. Thank you. Okay. So first of all, thank you very much for giving the invitation. Okay. And so what I'm planning to do in these 3 lectures is to give an overview of the developments involving D-instantons. Okay. So lecture 1, I'll try to give the general overview. And then lectures 2 and 3, I'll try to do some explicit computation. Okay, and part of lecture 1 may spill over to lecture 2, but we'll see. And I should say that please feel free to ask questions anytime you have one. So we'll begin by considering Venetian amplitude, which is how string theory started. So let's consider Venetian amplitude. I'll write this as an integral over the worldsheet because that's the way normally string amplitudes come. So physically, this describes a scattering of 4 open string tachyons. Of momenta P1 to P4. Okay, I'll use a convention where momenta are all ingoing. So an outgoing particle will have momentum minus Pi. And as you can see from here, that this diverges for 2P1 dot P2 less than or equal to -1, or 2, sorry, this should have been, it doesn't really matter how, 2P2 dot P3 less than or equal to -1. Okay, because this is a divergence from the y equal to 0 end, and when this happens, it diverges from the y equal to 1 end. And these are physical values of momentum, because in Y convention, where the metric is mostly plus signature, this is what we call S, right, or minus S. So this corresponds to S greater than 1. Now, the usual approach that one takes is to define the amplitude for 2P1 dot P2 greater than -1 and 2P2 dot P3 greater than -1, and then analytically continue to other regions. And this is in fact very common in string theory. Okay. So most string amplitudes are of this kind. Have this feature. So we write an amplitude as integral over the some moduli space of Riemann surfaces, okay, with vertex operators. So these include the moduli of Riemann surfaces as well as the locations of the vertex operators, say n of them, and then some integrand I, m1 to mn, okay, and these diverges from regions where the Riemann surface degenerates. And we again have to invoke analytic continuation to define these integrals, right? Namely, we define it in a region where it's well defined and then analytically continue to other regions. Now, what I'll describe today is a somewhat different viewpoint to this, okay? And that's based on Stringfield theory, okay, which in the short form we call SFT. This gives a somewhat different viewpoint. So let me say a few words about what Stringfield theory is, although later on we'll discuss some more detail. So for the time being, you can think of Stringfield theory as a regular quantum field theory. A regular QFT with infinite number of fields. And this Stringfield theory is designed so that its Feynman diagrams give the usual string amplitudes, at least formally, okay, which you get from integrals over the worldsheet variables. I'll make it clear what we exactly mean by formally. In particular, in a quantum field theory, you have a sum of Feynman diagrams. So each Feynman diagram gives integral over part of the moduli space. And the sum generates the whole integral. Now, given this, okay, we may ask how exactly do we get integration of our moduli space of Riemann surfaces starting with Feynman diagrams? Okay, because for Feynman diagrams, you normally do momentum integrals, okay, and not integration of our moduli space of Riemann surfaces. So, how do we get integral over moduli space of Riemann surfaces from Feynman diagrams? The MIs that we saw from Feynman diagrams. So MIs are the generalizations of the Y that you saw in the first slide. Okay, this is the general notation that I'll be using for the Y, for the worldsheet variables. Okay. So for this, let's consider in a QFT, what we normally refer to as the Swinger parameter representation. Parameter representation of a propagator. So what is Swinger parameter representation? That is simply this relation. If you take a propagator which has the form k square plus m square inverse, you don't care about the numerator factors right now. Then you write this as integral 0 to infinity ds to the minus s times k square plus m square. And often we'll also write this as integral 0 to infinity dq q to the power k square plus m square minus 1, okay, where q is e to the minus s. Okay. So in a quantum field theory, once this is done, the momentum integrals can be carried out easily. And you are left with integrals over the SIs. Okay, one for each propagator. So for each propagator, we introduce a variable s, and then you are left with integrals over those. Now, in string field theory, something very similar happens. In string field theory, something very similar happens, except that in string field theory, because you have infinite number of fields, there are infinite number of factors of this kind, infinite number of possibilities, k square plus mi square inverse, and you have to invert them. So it's more convenient to encode that in terms of an operator. So in string field theory, the role of k square plus m square, k square plus m square, is played by L0, okay, which is the zero mode of the Virasoro operator. Zero mode of the Virasoro operator. More precisely, what it means is that the eigenvalues of L0 gives you the k square plus mi square, okay, for different states, different string states. And now one finds that once we do this, we can carry out the ki integrals, carry out momentum integrals, again as before, as in a normal quantum field theory. And also sum over all internal states. Okay, that's another added bonus in string theory, that the sum over internal states can also be done explicitly once you use the Swinger parameter representation. Okay. And then the QIs that are left, the QIs integrals that are left, become the integral over the MIs after appropriate change of variables. Okay, and string field theory tells us the precise change of variables that you have to make. Okay, and we'll see examples of this in the later lectures.
About this Virasoro generator. So
yes.
So usually we have a Virasoro constraint. What happened in the string field theory? Is there some...
Virasoro constraint meaning ln acting on the physical state constant? That's what you mean? So the physical state constants are not present because string field theory deals with off-shell states, right? So in the internal state, everything propagates. Okay? We have the level matching condition L0 minus L0 bar equal to 0. That's part of the specification of string field theory. but we don't put any physical state constraint, namely the states have to be primaries, etc., because you sum over all internal states.
I see. Okay, thank you.
Because we are really dealing with off-shell field configuration. In the internal, just like in quantum field theory, in the internal state, you don't impose any on-shell condition, right? So in string field theory, you don't impose on-shell condition in the internal states. Is that okay?
So you yeah. So for external momentum, you have to only impose this Virasoro constraint, like is it?
For external momentum. For external momentum, you have to impose Virasoro constraint. That
Okay.
k square plus m square have to be on-shell. Exactly.
Thank you.
Okay, so in this language, you can ask where do the divergences come from? Okay. And what one can show is that all divergences come from qi goes to 0 region limit for one or more qi's. So the usual divergences that we see when integration of the moduli of Riemann surfaces, like the ones as y goes to 0 or as y goes to 1 that we saw in the first slide, can all be traced to the qi goes to 0 limit for some propagator. So let's now see where can qi goes to 0 limit diverge, right? What does it mean that you have divergence from qi goes to 0 limit? And so for that, let's recall how the qi's come. Okay, so the relation that we'll be using here is 0 to 1, q to the power L0 minus 1 dq. So you have replaced the k square plus m square by L0 because L0 eigenvalue is k square plus m square. Now, if you examine this relation, we can see that this is an identity for L0 greater than 0 states. Okay? Because for positive L0, okay, the right-hand side is manifestly finite. This integral can be done, and you can explicitly check that this integral indeed is, sorry, L0 inverse. 1 over k square plus m square, right? Is L0 inverse. So you can check that this integral is really L0 inverse. For L0 negative, the left-hand side is finite, but RHS is infinite. RHS is infinite because this integral diverges from the q equal to 0 n, right? That's precisely where we see divergences in the string amplitudes. So you see that one of the divergence, a class of divergences that we encounter in string theory can be simply traced to having states with L0 less than 0 propagating in the internal state. So in this case, string field theory has a very simple solution. In this case, SFT tells us to use the left-hand side. Right? Because that's where you started, 1 over L0. Okay? So what it is saying is that what is breaking down here is the Swinger parameterization is breaking down. This is not the correct relation. But as long as you continue to use L0 inverse, you will get the finite result. And one can show that this is equivalent to analytic continuation. Equivalent to analytic continuation. Where it exists. Okay, when analytic continuation is possible on the string theory side, on the worldsheet side, you can show that this procedure that string field theory tells us is equivalent to analytic continuation. But if we take L0 equal to 0, then both sides diverge. Okay, you can see also easily from here, okay, that this side, of course, is infinite, and this side is logarithmically divergent from the q equal to 0. Right? So both sides diverge. Okay. So in this case, there is no easy solution. Okay. you have to encounter the divergence. Okay. But what you can do in such cases, that in such cases, insights from QFT tells us what to do. Because what L0 equal to 0 state in the internal line means, okay, that basically we have an on-cell internal state, right? On-cell internal state. And in QFT, when you encounter an on-cell internal state, you typically know what to do. Okay, that you are either doing something wrong or that is a simple way to get around it. So example, okay, so it could be as simple as just an I epsilon prescription. Okay, so this could be as simple as I epsilon prescription. Okay, in the momentum integral, you just put I epsilon to deal with internal lines going on cell. But it could also be more complicated. But it could also more complicated. Because in QFT, when you have internal propagators going on shell, we can have other reasons than which cannot be solved by I epsilon prescription. Okay? And examples are collective coordinates. Okay, and this we'll see explicitly. When you have collective coordinates, we cannot deal with by Feynman diagram. Okay, we have to explicitly carry out the path integral of our collective coordinates. Or you can have a breakdown of gauge choice. And all of these we'll see explicitly, we'll encounter explicitly in our analysis. Okay, that when you have if the gauge choice breaks down, then the further forward determinant may acquire a zero eigenvalue. Okay, which if you are not careful will appear as if you have an on-shell 1/0 in the ghost propagator. But again, we know how to deal with those cases in quantum field theory because you have the standard insights of quantum field theory.
Collective coordinate meaning collective coordinate for some coherent states?
Yeah, so suppose you have a soliton, right? You are trying to quantize, do calculation in the presence of a soliton, which has a collective mode. If you just naively try to do Feynman diagram, it will look like a massless mode, right? And if you try to do Feynman diagrams, you'll get a 1/0 from those modes, or you'll get infinite divergences from those modes. But we know the way to deal with collective coordinates is that you separate out the integration of our collective coordinates outside the path integral. And after you do all the calculation using Feynman diagrams, then you have to finally integrate over the collective coordinates of the soliton. Whereas if you try to do naively using Feynman diagrams, which is what the worldsheet formalism gives us, you will encounter infinite divergences corresponding to having on-shell internal propagator. Is this okay?
Yes, thank you.
Okay, I mean we'll see also this explicitly during our analysis, right? All of these will appear during our analysis, and we'll see that the standard worldsheet method of analytic continuation fails, whereas Stringfield theory gives you a compact answer. Okay, compact and unambiguous answer. That's what is more important. So what we plan to do in these lectures, we shall apply SFT techniques to compute D-instanton amplitudes for which analytic continuation fails. Okay, and I will explain why it fails. So let me briefly describe what D-instantons are. So D-instantons are also known as D-1 branes sometimes, but I'll use a more general definition. So D-instantons are like D-branes. And it has the property, this is the general definition of D-instanton I'm going to use. These are D-branes with Dirichlet boundary condition. On all non-compact directions. And this includes Euclidean time direction. Okay, so these are D-branes in Euclidean spacetime. Okay, and you put Dirichlet boundary condition on all the non-compact directions. Along the compact directions, you may have either Dirichlet or Neumann. Okay, it doesn't really make a difference. They will give different kinds of D-instantons. So physically, these represent saddle points of the Euclidean path integral. Collectively, they represent saddle points of Euclidean path integral. And they give non-perturbative contribution to string amplitudes. Of order e to the minus c by gs, okay, where c is some numerical constant typically, and gs is the string coupling. Okay. And this follows from the fact that just like normal D-brane tension goes as is proportional to 1 over g string, okay. D-instanton action is proportional to 1 over g string. Okay. So the c over gs is precisely D-instanton action. Okay, and this we can calculate by the standard procedure that you use to calculate the D-brane tension. And so the advantage, okay, or the good thing about D-instantons is that it gives non-perturbative contribution to string amplitudes, okay, but it uses worldsheet techniques. Because everything is calculated as integral over moduli space or Riemann surfaces, okay, except that for D-instantons, you have the Riemann surfaces will have boundaries, okay, because they are a boundary condition that you put corresponding to D-instanton. But otherwise, it's just the standard integration over the worldsheet moduli that is involved in computing D-instanton amplitudes.
I have a question. So when you say Euclidean path integral, does it mean Euclidean path integral in the Stringfield theory or some other?
Yeah, it's some Euclidean path integral, we can say in open-closed Stringfield theory. But the details will not be very important because, as I said, I mean, you can actually calculate everything using the worldsheet techniques.
Okay.
Stringfield theory will be needed, okay, to make sense of the divergences. But otherwise, you will just use the worldsheet answers. So you'll never really need to write down the full string theory in whose path integral gives the D-instanton amplitudes. Okay, where the D-instantons will actually appear as saddle points. Okay. I believe you can, in principle, do it if you include open and closed field theory of open and closed strings, but it will not be necessary for what you are going to do.
Okay.
So as you will see, the string field theory will be used somewhat minimally. Okay, we'll try to make as little use of string field theory as possible. because that's not something many people are familiar with, and also it's not something that is needed. You don't need you need the full technology of string field theory to address the problems that you are going to address. Okay, so now let me tell the problem. Okay, what is the problem that one faces? So the problem that one faces in dealing with these D-instanton amplitudes, and we'll see this example in examples. These are the open strings on the D-instanton. Okay, or I should have said open strings whose ends lie on the D-instanton. Okay, that's how we describe events. They do not carry any continuous momentum. And the reason that they do not carry any continuous momentum is because you have put Dirichlet boundary condition on all the non-compact directions. So in those directions, the momentum vanishes. And in the compact directions, if you have Neumann boundary condition, you can carry some momentum. But those are all discrete. Okay, they are quantized. So there is a continuous momentum that you can adjust. And as a result, we cannot analytically continue in momentum. To make sense of divergences. That we normally encounter. And this is why we'll need a string field to tackle these. So we are going to illustrate this in a specific class of examples. Of two-dimensional bosonic string theory. I'll explain what that is. But let me emphasize at the beginning that the techniques that I'll be describing, okay, that will be valid for all kinds of theories, D-instantons in any theory, including critical superstrings, for example. And the problems that we'll encounter in this analysis, okay, will also be common to all string theories, or at least most string theories. Okay, that you will encounter similar kinds of divergences that you will see here in also critical superstring theories. And I'll also explain why we deal with two-dimensional bosonic string theory. Okay, but let me just say what this is. Okay, what the two-dimensional bosonic string theory is. Okay. So the world sheet theory here has a scalar x, scalar field x, describing Euclidean time coordinate. And a Liouville field theory which you can call phi of central charge 25. And as is standard in a Liouville theory, I mean, even though you have a single scalar, the reason that you have a central charge is because you have a linear dilaton background. Linear dilaton background along the Liouville direction. Okay, if you are not familiar with this, it's just enough to know for our purpose that it's some two-dimensional conformal field theory with total centers as 25. So the total matter central charge, so total central charge of the matter theory, central charge of the matter theory adds up to 26. And we also have the BC, B bar, C bar, the standard Gauss system, have C equal to minus 26. So the anomaly is cancelled. Just like in critical bosonic string. Okay, so you can really think of this as a critical bosonic string theory with a somewhat strange matter CFT. Now there's an added advantage here, and that is that the usual closed string tachyon that you are familiar with, closed string tachyon, becomes a massless field due to the linear dilaton background. Okay, again, you can see this by doing explicit spectrum analysis. But if you are not familiar with this, again, just take this as a fact that what we normally call the closed string tachyon, okay, is actually a massless state in this theory. And because of this, this theory is at least part arbitrarily consistent string theory, okay, because there is no tachyon in the spectrum. So you can calculate all the string amplitudes explicitly. Now let me say about why 2D string theory. So why this particular theory? And the reason is that this theory has a dual matrix model description. Has a dual matrix model description. That gives exact results. So in a sense, the answer is already known from the dual matrix model description. So this means that we can check string theory results against the matrix model results. So in particular, if you are going to use new techniques to study string theory results, and that's what we'll be doing in dealing with D-instanton amplitudes, then it better be that you first study it on theories where the answer is known from other considerations. And this is one such theory where the answer is known from the dual matrix model description. So whatever techniques we use to analyze this from the string theory side, we should be able to check against the matrix model results. So this is one of the motivations for why this, we are going to look at this two-dimensional string theory. But it is also the motivation why this paper that I'll be, whose result I'll be using extensively, the paper by the Harvard group, Balthazar, Rodriguez, and In. Okay, that's in 1907.07688. Studied D-instanton amplitudes in this two-dimensional string theory. So in the next few slides, I'm going to review what results they found. So what they computed is 2-point scattering of closed string tachyons. So 2-point amplitude of closed string tachyons. Okay, later on I'll also describe the n-point amplitude, closed string tachyons. Due to D-instanton. So the leading order result, okay, and we'll explain what we mean by leading order D-instanton amplitude. This comes from the following diagrams. Okay, I'll draw the diagram. 2-point function, remember, so there's 2 vertex operators. And the result that they found was e to the minus 1 over gs n. I'll explain the various factors. 2 pi delta omega 1 plus omega 2 to sine hyperbolic pi mod omega 1 Okay. So what are these? These are disk 1-point functions. Okay, so disk, the boundary of the disk has D-instanton boundary condition. Product of 2 disk 1-point functions. And this exponential of the annulus, so this is the annulus partition function. This means that you can have either no annulus insertion or 1 annulus insertion or 2 annulus insertions, and this way infinite number of annulus insertions. That's what is encoded in this exponential of this. So let me explain these various factors. So e to the minus 1 over gs, this is 1 over gs is the D-instanton action. Okay, the gs has been normalized, so that the 1 over gs is the D-instanton action. So that's where this factor comes from. This n here is the exponential of the annulus amplitude. So this n is this one. This is the energy conserving delta function. Okay, so omega 1 and omega 2 are the energies of the incoming and outgoing particles. So I'll be treating all the energies as ingoing, as we mentioned in the previous, in the first slide. So this may omega minus omega 1 is the energy of one of the particles, and omega 2 is the energy of the other particle. So let me call this 1 and 2. 1 and 2. Now let's look at and these factors, okay, these are the Liouville part of the correlation function that is coming from this disk 1-point function. So that's why you have 2 factors like this, sine hyperbolic pi mod omega 1 and sine hyperbolic pi mod omega 2. Now let me count the powers of G string. Okay, this of course is just the D-instanton action. But other than that, let's just count the powers of G string. So disk, because it has Euler number 1, okay, and because the string amplitudes are always carry factors of gs to the minus chi, minus the Euler number. So this comes to the factor of gs inverse. And then the closed string vortex operators, okay, closed string tachyon, but these are really massless fields. Okay, so I should probably put this in quotes. Closed string vortex operators, we will use the normalization convention where they carry factors of G string. So this gives you GS inverse times G string, that's of order 1. And this is similarly GS inverse times G string of order 1. And Annulus, okay, has no vortex operator insertion. It has Euler number 0. So this is order GS to the 0. And because it's of order GS to the 0, that's the reason why you have to allow arbitrary number of insertions of this annulus, right? That's what is responsible for the exponential of the annulus amplitude, annulus partition. Okay, and that's what you're calling this normalization factor n. I'll write down the expression for n in a few minutes. Are there questions?
Is the integration over D-instanton positions?
Okay, so that actually generates this one, this delta function. Okay, I'm going to explain this in the next slide. The integration over the D-instanton position is what is responsible for this. So in a sense, you have already done the integration over the D-instanton position. Worldsheet results, in a sense, already does the integration over D-instanton positions, but in a somewhat hidden way. Okay, and we'll see this later. So there is no further integration. This is the full answer that we have.
So the translation, allowed translation is along time direction only.
Yes, because in the Liouville direction, the translation invariance is broken, and the D-instantons are in fact localized in the Liouville direction.
Right. Thank you.
Yes. Okay. Now there are some issues which may look a little surprising. So the first is, why are you including disconnected diagrams? Why are you including disconnected diagrams? Disconnected worldsheet. Now, in general, of course, you have to include everything. Just like in quantum field theory, you have to draw connected and disconnected Feynman diagrams. But normally, the reason that you don't include disconnected diagrams is because one would expect that in a diagram like this, there will be separate energy momentum conservation, right? And as a result, this will, naive expectation will be that this will have delta omega 1 times delta omega 2, because there are two disconnected diagrams, and hence it will not contribute at a generic for generic omega 1 and omega 2 that just satisfies one energy conservation law. But what happens here is that because D-instantons, since D-instantons break time translation invariance, break time translation, symmetry, there is no separate energy conservation on each of these worldsheets. In fact, the 2 pi delta omega 1 plus omega 2 that we wrote down, this comes at the end after integrating over the D-instanton position. And that's the reason why we have to include this in this case. Okay, this in fact contributes at the same level. Okay, or, I mean, this is no this contributes as a generic point in the kinematic space, just like other diagrams. The second question one might ask is that why are you including bubbles? Including bubble diagrams. Right, like exponential of this annulus is like a bubble diagram, right? So normally we don't, these are supposed to factor out from numerator and denominator in a path integral. Right? So why are you including bubble diagrams? And this can again be seen as follows. Okay, so here, remember the D-instantons are non-perturbative contribution to the path integral, but there is also a perturbative contribution. So the actual physical amplitude you can write as the perturbative amplitude, okay, including all diagrams, okay, disconnected bubbles, everything, plus e to the minus 1 over gs times 1 instanton correction, and then there are of course higher order instanton corrections, which we'll not worry about. And you have to divide it by the total vacuum amplitude that involves the perturbative bubbles, okay, the world sheet with no external state, okay, just include the closed Riemann surfaces, integration over closed Riemann surfaces. Then there are non-perturbative bubbles, the D-instanton bubbles, okay, e to the minus 1 over gs times bi, and then again higher order terms. Now, when you expand this out in parts of e to the minus 1 over g string, you see that the leading contribution is AP over BP. Right? And this has the interpretation that you are just using the perturbative diagrams, right? Summing over normal Riemann surfaces, and you are factoring out all the bubbles, perturbative bubbles. So here, we don't include any bubbles in the perturbative diagrams. Then we have e to the minus 1 over gs. This contribution has two terms. One is AI over BP, and minus AP over BP times BI over BP. AI over BP, this has the interpretation that you remove perturbative bubbles, the bubbles which have no boundary ending on D-instanton. And that means that you, for example, shouldn't include diagrams like this. If you have a perturbative bubble like this, these are bubbles of closed strings only. These should be excluded. Okay, so you shouldn't include those. This subtraction, okay, if we just think about it a little bit, okay, you can see that this subtracting from AP over BP from perturbative amplitudes, the instanton bubbles. Which means that what this is subtracting is that if we take a sphere amplitude, say 3-point function on the sphere, times a instanton bubble, okay, an annulus, this also should be removed. Okay, this subtraction basically removes these diagrams. So this is also not there. But there is no subtraction of these diagrams, of a diagram like this, and this. Right? There is no subtraction of these diagrams. So these are to be included, right? And that's what we have done. Okay, so this is something you should keep in mind, that is the reason that you have to actually include the bubbles. Is this okay? Are there questions? Okay, so now let me give the result for n. Okay, everything else has been given explicitly. So n, okay, which is the exponential of the annulus amplitude. Annulus amplitude, of course, can be written down explicitly, okay, and it has this form. And now we see the first instance of a divergence, that this one diverges from t equal to infinity n, right? And in fact, S, the Swinger parameter that we introduced earlier, is really 2 pi t. So this corresponds to S goes to infinity, or equivalently q equal to the minus S going to 0. So this is the first example where you see that there is a divergence in the instanton result. And you can see that the exponents are totally independent of any external momentum. And so there is no way to define this integral by any analytic continuation. So analytic continuation fails and you have to deal with this. No analytic continuation possible. And one of our goals will be to extract a finite result out of this.
Can I ask a question?
Yes, go ahead, please.
In Bosonic string theory, when you have D-branes, you also typically have open string tachyons. Are there no tachyons here? Because
yes, indeed. This is yeah. So this is the result of the tachyon.
This is related to.
So this is coming from the tachyon propagating in the loop.
Okay.
And this is
sorry, yeah, it's a real tachyon. It's not massless in this case, like the closed string one.
No, it's a real tachyon, exactly.
Okay. Thank
you. So that basically shows that the D-instantons are saddle points and not a minimum of the action. Okay, but we have to still include the contribution from the saddle points in the path integral. Is that okay?
Yes, thank you.
Okay, thank you. Okay, so now let me describe the result of the next order. So next order, there are 3 classes of diagrams. By next order, I mean next order in G string. Okay, and we'll make it more explicit later. So the first class of diagram is this one. Okay, I should just not draw this. Okay, maybe I'll write it once. So exponential of this is always present. Okay, because you can always, given any diagram, you can always add arbitrary number of annulus without any cost in GS. So this one is next order. Why is it next order? Because you see that this will be of order. The disk will give 1 over GS. Okay, there is only one disk, and then 2 closed string vertex operator. That gives you GS times GS. So this is of order GS. And BRY explicitly computed this. Okay. And maybe I should have, let me give it a name. This tree-level result that we had. Okay, let me call this. This I'll call A naught. Okay, that's the leading incidence contribution. Okay, and I'll write everything else in terms of this A naught. Okay, so I don't have to write this again and again. So this is of order GS. So BRY wrote down the explicit form of this. And let me write this as A0. We'll always normalize with this A0 times the explicit factor of G string times a function of omega 1 and omega 2. And this function is given as a complicated integral because the Liouville theory is complicated enough that they didn't have the closed form expression for this 2-point function on the disk. They had to really write it as an integral over a conformal block. Okay, integration over Liouville momentum. But what they found is that this F actually has divergence. Okay, so let me write this here. It has a structure of this kind: 0 to 1 integral dy y to the minus 2 plus 2 omega 1 omega 2 y inverse plus F finite omega 1, omega 2. Okay. So this is a finite contribution. They know what it is, but it's given as an integral. So they can actually evaluate it only numerically. Okay, and that's what they did. That is, numerically evaluated it and studied this for as a function of omega 1. Right? Omega 2, of course, is equal to minus omega 1 because of this delta function that is sitting inside S. But this one you can see is divergent. Right? This has divergence from y goes to 0. This diverges from y goes to 0 n. Y goes to 0. Okay, physically we'll see this again explicitly later. But right now, let me just say physically y goes to 0 corresponds to one of the vertex operators approaching the boundary. Okay, so that's the singularity of the Riemann surface. Okay, so this diverges from the y equal to 0 n. And you see that the exponents are independent of omega 1 and omega 2. So there is no way to do an analytic continuation in omega and try to make sense of this divergence. Okay, you really have to deal with this head on. So at this stage, what we will do is we'll just parameterize this, okay, this part as AF plus BF times omega 1, omega 2. Okay. Where AF and BF are constants, so AF will be like the integral dy y to the minus 2, BF will be integral dy y inverse, both are divergent, but let's just write it as two constants. And our goal will be to actually compute these two constants. So other diagrams are similar, so let me quickly write them down. So you also have diagrams like this. So this is 1, this is 2. And then you also have another diagram where you exchange 1 and 2. Okay, where you put 2 here and 1 here. So this represents product of 1-point function on the disk and 1-point function on the annulus, and then arbitrary number of insertions of the 0-point function on the annulus. And again, the counting of GS is easy. This gives you GS to the 0. But here the annulus has GS to the 0, but the vertex operator has GS. So this is also of order GS. And then BRY wrote this as A0 times GS times G of omega 2 plus G of omega 1. Okay, so G of omega 2 comes from this diagram. So G of omega basically is the ratio of the annulus 1-point function to this 1-point function. And this one comes when 1 is inserted on the annulus and 2 is inserted on the disk. And again, they found the expression for G omega, okay, in terms of even more complicated integral. This in fact involves 2 integration over Liouville momentum and 2 integration over the moduli. But what they found is that this has a divergent piece which can be isolated, okay, where the Liouville momentum integrals are not there. Plus G finite. So this finite part is a complicated integral. Okay, it involves integration over not only v and x, okay, weighted by various theta functions, but also integration over the two Liouville momentum. Okay. But this is finite, so they can in principle evaluate it by numerically. Okay. But you see that this diverges as v goes to 0 and x goes to 0. So this diverges as v goes to 0 and x goes to 0 and or okay, x goes to 0. So v goes to 0 corresponds to the case where the annulus becomes long. Okay, so this circumference becomes much larger than the width. So that's the degeneration of the annulus, and the x goes to 0 corresponds to the region of the moduli space where the vertex operator approaches the boundary. Okay, so both represent singular kind of Riemann surfaces, and that's where the divergences come from. And again, at this stage, all you can do, okay, is to label this as AG plus BG times omega square. Okay, where AG is this quantity, the integral of this, and BG is the integral of 2V inverse. And we'll later on try to make sense of this AG and BG, okay, as from Stringfield theory perspective. And finally, we have the third class of diagrams, which are in fact simpler in one way, in one sense, but also more complicated in another sense. So that's this one. We have product of disk amplitudes, exponential of the annulus. This is the leading contribution. And then you multiply this by a partition function, 0-point function, where you have disk with 2 holes or a torus with 1 hole. Both of these have Euler number -1. So they give contribution of order GS. These, of course, have GS to the 0. So this we can parameterize as A0 times GS times some constant C. Okay. This doesn't have any dependence on any of the energies. Okay. That's why it's just a constant C. Okay. So this, in principle, one can write down the explicit expression, but this has not been done. Has not been written down. Okay. But this is also divergent. Okay, just from general argument, one can show that this will have divergences whenever the Riemann surface is degenerate. So with this, let me now write down the total to this order. So total contribution to this order is A0 times 1 plus GS. I'll write it as a finite part and the infinite part separately, a finite omega 1, omega 2. So in writing this, you see that BF and BG have combined, and that's because we used omega 1 equal to minus omega 2. So that omega 1 squared and omega 2 squared both can be written as minus omega 1 omega 2. Okay? That's how it became, it was BG omega 1 squared plus BG omega 2 squared, but it became minus 2 BG omega 1 omega. So at this stage, okay, this A naught, the overall normalization is not known, N, right? And then because that's divergent, okay, these are of course explicitly computable. Okay, these are all finite integrals, and these are not known. The matrix model, of course, gives the exact result. Okay, so in the matrix model, it is known. This is a known function of omega 1 and omega 2. Okay, in particular, known function of omega 1 because you have the energy conservation. So what BRY did was to compare this with the matrix model to find out the unknown constants. So comparison to the matrix model, comparison with matrix model. that gave n. Okay, n can be determined analytically because here there is no approximation that is needed. A naught is physically known in terms of n. And they also found this is AF. These combinations AF plus 2AG plus C and BF minus 2BG. So I'll give the results in a few minutes. Okay, but these are obtained numerically. Okay, by doing the best fit of this function with the matrix model result. So I'm going to give the result, but I'm going to do this after a few minutes after I generalize this. So it turns out that one can use the same data. One can use the same data to compute n tachyon amplitude. Okay, again tachyon in quotes because they are really massless particles. So the leading contribution comes from the product of disks. And then exponential of this. And from what I have described, one can easily write down the result for this. It's n e to the minus 1 over j, the same n, right? Because the same exponential of the Annulus. And then you have 2 pi. This time there is a overall delta function, which is omega 1 plus omega n. And then you have this product of the 1-point function for the Liouville sector. So this one I'm going to call, this whole thing I'm going to call A0n. Okay, just to say that this is the leading endpoint function. Okay. And it doesn't require any more data than what you already had for the leading 2-point function. So at the subleading order, again, there are 3 types of contributions. So first is n minus 2 disk 1-point function and 1 disk 2-point function. Okay, you can easily convince yourself that these are all of order GS. Then n minus 1 disk 1-point function and 1 Annulus 1-point function. And the third one is n disk 1-point function times those two, the disk with 2 holes and then torus with 1 hole. And all of these, of course, multiplied by exponential of the Annulus partition function, which I have not even said. Okay, so all of these have the exponential of this. And you see that the ingredients that we need, okay, are exactly the ones that we have already encountered before: the disk 2-point function, Annulus 1-point function, and then this one. So you don't need any new functions or new constants to write down the results for this amplitude. Okay. The new ones are, for example, a disk 3-point function, right? You could have an n minus 1, n minus 3 disk 1-point function and a disk 3-point function. But that you can show is order gs square because the disk 3-point function gets a 1 over gs from the disk and 3 factors of gs from the 3 vertex operators. That becomes order gs square. So to order gs, these are the only 3 contributions. And based on this, I'll write down the result for the amplitude. So the result that BRY gets is AN0 times 1 plus GS I less than J if, let me write this and then I'll write the next step. Okay, this is easy, right? That's just, I mean, from that summing over diagrams, you can get this. And this you can now write as a sum of the finite piece and the divergent pieces. Okay, and that's what I'm going to do now. So 1 plus GS. Okay, so let me first write the finite pieces, where you just replace these by finite ones. If finite omega I omega j plus sum over ig finite omega I plus c, sorry, no c will go in the divergent part, plus n into n minus 1 by 2f okay, just substituted the f and g in terms of its finite pieces and the infinite pieces. So this part is completely known, okay, although numerically. These are unknown constants. And now you notice that if we look at this for different values of n and compare the matrix model result, so let me write this here. So the matrix model result for this is known. Matrix model gives the exact result. Okay, maybe I'll show you at some point at the end of today's lecture the matrix model result. So you can just compare these two and determine individually AF, AG, and C by comparing this for different values of n. And this one you can see that it always appears in this combination of BF minus 2BG. And that's because of this, because A0n contains the energy conserving delta function, the sum over I omega I square can always be written in terms of sum over I less than J omega I omega J. Right? And once you do that, then it's the combination BF minus 2BG that appears. So let me give the BRY result for this. This in fact is unpublished. Okay, the published version only does a comparison for n equal to 2. So n is minus 1 over 8 pi square. Okay, this is analytical because this requires only leading order comparison of the leading order results. The rest are numerical. So AF is minus 0.50, AG is 0.00, C is 0.00, and BF minus 2BG is 1.40. So these are numerical results, okay, and the error in each of these is like plus minus 0.01. So our goal will be to describe how to compute each of these from string field theory. Okay, because as we have been arguing that in principle, string field theory should be able to give finite results for all of these without any without invoking the matrix model result. And let me give the results so far. So results of string field theory of SFT so far. These are all analytical results. So log 4 is roughly 1.38, 386, I think. So you see that, and C, okay, C has not been computed explicitly because it's just C is difficult to calculate, right? There is no analog of the expressions that I wrote down for F and G. But once one writes down an expression for C of that kind, you can easily use string field theory to extract a finite answer. So C has not been calculated for that reason. Okay. But there are indirect arguments which shows that C should vanish. Okay. So I should say that these indirect arguments indicate that C should be 0. Okay, I mean, I have confidence in these arguments because these arguments were found before the actual numerical results came.
Ashok, can I ask one question?
Yes, go ahead, please.
AG looks definitely some
that's the
discrepancy. I see.
Exactly.
It's
So
not typo.
No, it's not a typo.
Okay.
So this is the black mark. Let me color it properly. So this, okay, seems like a disagreement. We don't know what it is, how the disagreement comes through. The simplest explanation is that I have made a mistake in the string field theory calculation. Or maybe that there is some subtle effect in string field theory that has been missed, right? Or maybe there is some subtle problem in the matrix model calculation. Okay, but most likely one is that there is some simple mistake in the string field theory calculation. Okay, but so far I have not been able to find this. So I expect that this will be eventually resolved. Okay, that it cannot be that everything else agrees and AG doesn't agree, but at present AG doesn't agree. Okay, so that's where things stand at present. Are there questions on this? Okay, so now maybe what I'll do, since it's almost near the end of time, I'll show you the matrix model result and then I'll stop because matrix model result is very explicitly obtainable. So let me see if I can get this. Yeah, so this is a matrix model result. Okay, maybe I do full screen. So this is what you already saw. Yeah, this is a D-instanton contribution. And here is what the matrix model gives. Right? You can see that here explicitly, everything is explicitly given. Right? There is an ambiguity, everything is finite. And so the idea is that you evaluate these numerically, okay, and then find the best fit values of the constants. You have to do this for different n, right? So you have to compare this for different n, okay? And then you find the best fit values of the corresponding constants. And using this for each n, you will get one particular combination of A, F, A, G, and C. But if you span it over different n, then you can combine the results to get the individual results for A, F, A, G, and C. And that's what gives the results that I quoted at the end of this lecture. Right? So that's what gives, maybe I have it here also. Yeah, these results are what I showed you. And this is the BRY result, right? And Stringfield theory results for comparison. Yeah, here is the, you can find the full comparison. The Stringfield theory gives you AG equal to -half, whereas the matrix model seems to suggest that AG should vanish. Okay, so I think that's where I'll stop today. And from tomorrow and day after, I'll try to give some more details of the calculation. So I'll start with N, because in a sense that's technically the simplest, but conceptually I think that it's the hardest, because in the history that was the one which was calculated last. Okay, because conceptually the calculation of N is the hardest. So I'll start with there, okay, because it's technically simple, and then I'll go on to describe the calculation of F and G, okay, to whatever extent I can. Okay, so I think I'm going to stop here. Are there questions?
Ashok, can you sort of get back from the beginning of this about the divergence itself?
Yes, okay.
So, I mean, in field theory, even if we use I epsilon prescription, which is,
Yes.
I think is like going to Euclidean regime, say.
Yes.
And if I do Schwinger-Dewitt, method, I do end up with, typically UV divergences. Are these divergences you see are analog of those UV divergences or something?
No, these are not UV actually. These are all IR.
I see.
Because you can see the divergences that we see are coming from on-shell states. Let me, yeah. See, the Q goes to 0 divergence, right? Are all coming from on-shell states. When k square plus m square is, okay, either on-shell or tachyonic. Okay, maybe I go a little, okay, in this language, right? So for L0 larger than 0, there is no problem, right? That's k square plus m square positive. For L0 less than 0, also there is no problem. I mean, from the worldsheet perspective, that seems to be a problem because the Q integral diverges. But from the Stringfield theory perspective, there is really no problem, right? Because it's an L0 inverse. The problem comes from the L0 equal to 0 states, because both sides diverge, and those are like on-shell internal states. So in Stringfield theory, all the ultraviolet divergences are cut off, because what one can show is that the Stringfield theory interaction vortices have exponential suppression for Euclidean momentum.
That's right.
So that makes everything perfectly ultraviolet finite. So there is no ultraviolet divergence from the Stringfield theory perspective. All divergences are infrared. Where by infrared, I mean the general version of infrared, which is on-shell internal states.
Okay, thank you.
I have a question.
Yes, go ahead, please.
So this calculation is you consider some particular sector of the matrix model, like
the singlet sector. Yes, that's what you mean. I mean, okay, on the matrix model side, what you do is that you calculate the two closed string amplitude.
Yes.
So those are by construction in the singlet sector, because the way you identify the closed string states with the matrix model, you already go to the singlet sector of the matrix model. Mm-hmm. So from this point of view, the matrix model, you can just think of this as an inverted harmonic oscillator potential and free fermions moving in that potential. Okay, that's the content of the matrix model. You don't need any details of the matrix model. Okay? And those free fermions have Fermi level filled up to a given point on one side, and the other side is empty. Okay, that's the matrix model that we are considering here.
Yes, but you can from the matrix model point of view, there could be more like other more not only singular sector, but also there are many other non-singular sectors.
Yes,
so,
but the point is, okay, those what they correspond to in string theory is not completely well understood. Okay? But I think there are some recent papers again by the same group, BRY, where they say that those correspond to changing asymptotic boundary condition. Those are like this FZZT brain, the space filling brains in the Liouville theory. And as you know, once you have space filling brains, you are basically changing the vacuum of the theory, right? The asymptotic boundary condition has changed. So here we are considering a particular asymptotic boundary condition. There's a Liouville field theory without any space filling branes. And those
I see.
correspond to this inverted harmonic oscillator potential as the one-side field.
Okay.
An instanton from the matrix model viewpoint, even though you don't, from the matrix model side, you don't get the result by summing over instantons. You have the exact result and then you do the expansion. But roughly the instantons correspond to tunneling from one side to the other side. Okay, so this action, for example, is the same as a D-instanton action.
I see. Okay, thank you.
Can I ask a question?
Yes.
In these 2D string theory models, can I think of D-branes and D-instantons in the same way as I typically think about them in critical strings, like a lamp localized in target space, in particular?
Yes, indeed, you can. I mean, so in Liouville theory, right? I mean, Liouville theory has this it's like half line, right? Liouville theory is a half line because there's a potential that prevents us from going to the other side. And the D-instanton, so this is Liouville and this is XA. A standard D brane will be a D0 brane will be localized at phi equal to 0. Okay? The D-instanton is localized at phi equal to 0 and x equal to 0. So it is like what you normally think of in standard critical string theory. Okay? So this is localized.
Mm-hmm. What is the boundary?
X, of course, can be anything, right? And x equal to, say, x naught. And at the end, you have to integrate over x naught. That's the collective coordinate integral.
Right. What is phi equals 0 corresponds to? Why is there a boundary there?
Well, because Liouville, there is a potential which prevents us from going beyond this.
So, okay, it's a kind of the, but the instanton is located there. There is no relation. There is no relation between phi and GS and the coupling GS.
No, phi is the worldsheet coordinate.
Right.
And the GS is the value of of the dilaton. Right? The dilaton as phi goes to infinity is the GS. As phi goes to infinity, okay, or e to the minus e to the dilaton as phi goes to infinity is GS.
I'm wondering what is the value of GS at phi equals 0? Which is where the instanton is localized.
Okay, yeah. The point is that this is a strong. I mean, okay, maybe I should say it this way: that you describe this region by an exact CFT. That you cannot have the usual interpretation of the weak coupling interpretation in this region, right? Because here the target space metric, the target space theory is strongly coupled.
Right.
And so GS takes some value because there is a linear dilaton, right? The dilaton is going down on this direction, but it's increasing in this direction, right? So it's, and the value of GS here is controlled by, of course, the value of GS at infinity.
Right.
But otherwise, you really cannot say what it is, right? Because it's a strongly coupled, from the target space viewpoint, it's a strongly coupled theory.
Right. I'm a little bit puzzled then how does the exponential of -1 over GS appears? Because typically I would think it's the tension of the brane, but if the D-instanton sits at strong coupling at a value where the the dilaton blows up, it's puzzling. I don't know.
Yeah, I understand your question. So the point is that you calculate this not by using weak coupling target space theory, but writing down an exact boundary state of the D-instanton in the Liouville theory. And that, given the exact boundary state, you can read out what the what the tension is.
Right. So a typical weak coupling evaluation, like we often do in critical strings at weak coupling, is not valid. It's not how you reach this result. That's
right. Yeah. So because this will be the analog of let me say it in this way, that suppose you have a Gepner model, right? And you have D-branes in Gepner model.
Right.
So those brane tensions have to be found by finding the exact boundary CFT. right? Exact
Right.
boundary state, and then that gives the tension, which is not the standard calculation in free target space theory, right? Where the x's are free, where you put this boundary condition by saying that there's a boundary condition x equal to constant there, right? You can do it for the x here, but for phi, you cannot say that phi is that you have Dirichlet boundary condition on phi, because phi is a strongly coupled target space variable near the origin. But you have an exact boundary state description, and that's how what one uses to calculate the tension of the D-instanton.
All right, I see. Yeah. So, but the final result, like the exponential of -1/GS, that GS is the boundary value, so it could be weakly coupled. So I can take the
exactly.
GS to be small.
Exactly.
Okay.
So that GS is defined from infinity.
Right. Perfect. Thank you very much.
Thank you.
I have another question.
Yes.
To understand this problem, does supersymmetry helpful, or is it maybe
No,
it's not?
Supersymmetry doesn't quite help. In type 2B string theory, if you do a similar calculation, you have exactly similar divergences. Type 2B D-instanton, for example, will have exactly the same kind of divergences.
And do they match, or
This
still
calculation
there is a discrepancy?
I mean, I can tell you the partial results that I have so far, that I know that they match up to including factors of pi and factors of string coupling. In fact, the matching of the string coupling was noted even earlier by the Harvard group, right? But I have to check that the factors of pi match, but factors of 2, I'm still trying to see whether they match or not. So this calculation has not been finished. I mean, for the type 2B, right, it's just a little more complicated calculation because of the more variables. But in principle, one should be able to do that in type 2B string theory as well. Okay, this is for the n. Okay, these calculations, in fact, the Harvard group is trying to do the analog of these calculations in type 2B string theory, and I think their work is still in progress.
Did you not say that one of the divergences arise from the tachyon, open string tachyon, and there is not such a tachyon in.
Yeah, you are right. But the point is, there are also divergences from the same n that we saw had divergences from massless states also.
Right, but you are saying that all of the divergences are equivalent. You could like.
Okay.
In the supersymmetric version, there should not be the divergence. This one that you say is related to the tachyon.
So this one will not be there. Right?
Okay.
The supersymmetric version, this one will not be there. Right? But this one will be there.
I see.
Because these are for the massless states. Right? And there are certainly a lot of massless modes in superstring theory. Right? Both in the Nabu-Schwarz and Ramon sector.
I see.
And those you have to learn how to deal with. In fact, the tachyonic divergences are easier to handle, right? Because as I described, they are like that you have, okay, in this case, it's log L naught, not 1 over L naught. But roughly when L naught is non-zero but negative, right? You know how to handle this. I mean, it's either 1 over L naught or log of L naught you can handle. It's the massless ones which are the hardest to tackle. And those are common here as well as for the superstrings. Is that okay?
Yeah, thank you.
Okay,
makes sense.
Any other question? Okay, so maybe I'll stop then. Let me stop sharing.